All right, the fundamental theorem of calculus deals with integrals, and in particular definite integrals and how you evaluate a definite integral. So you've already worked some definite integrals, but officially, I guess, technically, we haven't went over the definition of a definite integral. Here is the fundamental theorem of calculus. If a function f is continuous, everyone knows what continuous is, right? On the closed interval from a to b, so these are usually x values, and capital F, if the function is lowercase f, capital F usually stands for the antiderivative, so like your answer that you get out after you integrate. So capital F is an antiderivative of f on the interval from a to b, then the integral from a to b of f of x dx is equal to capital F of b minus capital F of a. So this is what we do whenever we evaluate a definite integral, is we take the answer and then we plug in the upper limit into our answer, minus we plug in the lower limit into our answer. That is the fundamental theorem of calculus. There are several ways that you can prove that. It involves a little bit more of a technical math than I usually cover in my calculus classes, but one of the ways is by going through with the mean value theorem, something you've seen before from Calculus 1. But remember, it's whenever you do a definite integral, you don't have to put plus c, the constant of integration. That's because if it just hurts you not to put plus c, and you're wondering, well, why don't I have to put plus c? Well, really here, whenever I evaluate that upper limit, I have plus c, and then I say minus, and I evaluate that lower limit, I have plus c. I wouldn't write this down, but I'm just showing you why. And so if you have a plus c here and a plus c here, and you're subtracting, then the c's are going to cancel out. So you don't have to worry about that constant of integration, because it cancels itself out every time. Okay. So I'm going to work just a couple more antiderivatives, definite integrals, and I'm going to work one type that you don't see a lot, but whenever you do see it, students usually have a little trouble with it. It's not going to be this first one that I work, but so the first one that I'm going to work is, let's see, the integral from 1 to 3 of the fourth root of the cube root of x dx. And so we want to make sure we always leave our final answers as exact as possible. So we simplify radicals, we leave all of our answers with positive exponents. We do all of that kind of stuff. So the first thing you'd want to do here is rewrite the integrand. Remember, the integrand is the thing that you are integrating. This 4 that's in front, you can bring it out in front of the integral and then just work with the integrand, and at the very end then just multiply the 4 back in. And so if I rewrite that integrand, this is x to the 1/3 power. Now the way that I integrate that, I add 1 to the power and divide by the new power. Okay, so notice I'm keeping that 4 out here. And then if I add 1 to the power, that'll be the 4/3 power. So I'm going to have x to the 4/3 power divided by 4/3. Evaluated from 1 to 3. Now I'm not going to keep it like that. That's that's a little too messy. It's going to be 4 times. So flip and multiply. So that'll be 3/4 x to the 4/3. And since that's a constant, you don't have to, but you can move that out in front. You can always take any constants out. Even at this point here, before you evaluate, you can take constants out. And I'm going to do that because you can see on this problem, if I bring out a 3/4 and I have a 4 there, 4 times 3/4 is just 3. So that's going to be 3 times, and now I'm evaluating that from 1 to 3. Alright, so this is 3 times, and when I plug in a 3, that's going to give me 3 to the 4/3 power minus 1 to the 4/3 power. Now that's not equal to 2 to the 4/3 power. Just because the powers are the same doesn't mean you can do anything. What you want to check and see is, can I reduce this, and can I reduce this? The two things you have here. Alright, so what does the 4/3 power actually mean? That means the third root of what? 3 to the 4th power. And so 3 to the 4th power is 3 times 3 times 3 times 3. Since this is a cube root, for every 3 of these factors, whether they're the number 3 or not, for every 3 of them you can bring 1 out. So that's going to be 3 cube roots of 3, and then 1 to any power, except possibly infinity or negative infinity, will always give us 1 to any power is 1. So it's just minus 1. So there's your answer in exact form. You may think, well, do I need to multiply the 3 in? You don't have to. You can. But anytime you can leave something in factored form and exact, it's best to do so. All right. Let's look at this example. The integral from 0 to pi over 4 of secant squared x dx. Alright, so we all know that the derivative of tangent is secant squared. So that means that the integral of secant squared is tangent. Right? Again, the derivative of tangent is secant squared, so the integral of secant squared is tangent. I want to evaluate that from 0 to pi over 4. So that's the tangent of pi over 4 minus the tangent of 0. The tangent of pi over 4, we all know is 1. That's like the tangent of pi over 4 is the same as the tangent of 45 degrees. We don't deal with degrees anymore. We've kind of graduated from that for the most point. So, for the most part, I mean. So that's going to be, again, just 1. And then minus the tangent of 0 is 0. Alright. So here's the integral I was talking about. You don't run into these integrals very often, but when you do, a lot of students get confused on them because, again, you just don't practice a lot with these types of integrals. And so, let me show you how to do the integral of an absolute value. And you may or may not have done these as an indefinite integral. I'm going to work one out as a definite integral. Alright, so to really understand why we do what we do when we integrate here, we need to understand a few things. We need to understand what does absolute value actually mean, or what does it actually do. And then we also need to maybe look at a graph so that we can see it in action and it'll make a little more sense to us. Alright, so what does absolute value actually mean? When you take the absolute value of something, if it's positive, you just get that something out, right? When you take the absolute value of a negative something, what happens? You just get the absolute value of that out. Okay, so we have two different cases that could give us the same answer. All right. Now that we understand, you know, I'm sure you understood that before, but just to refresh your memory on absolute value. It's almost like you could say if x is greater than 0, then you just get x, right? But if x is less than 0, you get out the opposite of what you put in. So again, that's just explaining absolute values. So it means the same thing the first way we went over it, second way we went over it. Just keep in mind that when you work an absolute value problem, if you remember or not, back from algebra, that you always have to work out two equations. And so that's going to have to come into play somehow with the antiderivative. You're going to have two something, two equations, two integrals, something like that. Alright, so I'm going to show you a sketch really quick of this 2x minus 1. Here's what it looks like. Okay, let me see if I can make that a little bit larger. Alright, and so with absolute value, the reason why you have to work out two equations again is because there's two different equations that can give you the same answer with absolute value. Why is that? Well, without those absolute value bars, this line right here, this line right here is 2x minus 1. And without the absolute value bars, you could get negative y answers. So without the absolute value bars, you would just keep extending this line down and it would go down to the left forever. But the absolute value bars say that no matter what you plug in, you can't get out a negative answer, okay? So that's why the graph bounces back up. Well, this line right here is actually, it's not 2x minus 1. This line right here is the negative of 2x minus 1. And so that's why the graph is V-shaped, because one of the lines is just the function without the absolute value bars, and the other line here, that's the negative of the function, okay? And so if we're taking the definite integral of this from 0 to 2, then 0 to 2, the lower and upper bounds of our integration, that's our x values. So you see right here from 0 to 2. And so I'm not going to be able just to use this one function here. If this is 0 and this is 2, I'm going to have to set this thing up so that I have the integral from 0 to whatever this value right here is, plus the integral from this value right here to 2. And that'll give me the area under this V-shaped curve. So 2 equations when you solve an absolute value problem, 2 integrals whenever you integrate an absolute value problem. All right. So we have to figure out what this place is. This is a little magical place for us here that's important because that's where we split up our integral. I definitely know it's between 0 and 2 because that's my entire interval. One easy way would be to figure out this right here, this value, this x value. What is y equal to when the graph touches the x-axis? 0. So what I could do to find this x value is I could just set the function 2x minus 1 equal to 0. And that'll give me what x is equal to when y is 0. All right. So, or the x-intercept of this graph. So 2x equals 1, so x equals 1/2. So this, just like it looks, is to scale, and that's a 1/2. Okay. So if we want to do the definite integral of this from 0 to 2, I'm going to have to integrate first from 0 to what? 1/2 of this function here. And what was this function? This was the one that was negative. So it's the negative of 2x minus 1 dx plus I'm going to have to integrate this function, this line, from 1/2 to 2. All right, and which function was that? That was the one without the negative in front. That was the 2x plus, or the 2x minus 1. All right, so let's do those two integrals really quick. So this negative you can just put on the outside and apply it at the end. That's what I'm going to do. And so then I'm going to just integrate that. So that's going to be x squared minus x. And then I'm going to evaluate that from 0 to 1/2. All right, and so that's going to be the negative of, and then I'm going to have 1/2 squared minus 1/2. That's what I have whenever I plug this 1/2 in for those two x's. And then I'm going to have minus, and then when I plug in the zeros, I get 0 minus 0. So plugging in a 0 on this does nothing. Sometimes it will do something, so don't take that for granted. Don't think it's always going to be 0. All right. So this is the negative of 1/4 minus 1/2. So 1/4 minus 1/2 is negative 1/4. 1/4 minus 1/2 is negative 1/4. But there's a negative on the outside, so the negative of negative 1/4, or just 1/4. Okay, so that's the answer to the first integral. Now let's figure out the answer to the second integral. I integrate the same way, except I don't have that negative in front there. So it's just going to be x squared minus x. And I'm going to evaluate that from 1/2 to 2. Alright, so that's going to be, when I plug in a 2, that's 2 squared minus 2 minus 1/2 squared minus 1/2. Okay? So that's 4 minus 2 minus, this is the same thing I worked out earlier, right? That's 1/4 minus 1/2. So 4 minus 2 is 2 minus, that's going to be a negative 1/4. Alright, so that's 2 1/4, or 9/4. Alright, my first integral was 1/4. My second integral was 9/4. So to work out that definite integral, I need to add those two together. So 1/4 plus 9/4. That's 10/4, or 5/2. So that definite integral is equal to 5/2. Alright, in one of the previous sections, we worked with area of a region under a curve. And the area under the region of a curve, depending on how you draw your rectangles, remember, when estimating the area under the curve, maybe you get an area that's larger, maybe you get an area that is smaller, depending on whether what endpoint you use, where your rectangles, if they go above or below the curve. You went over in Calculus 1 the mean value theorem. The mean value theorem in Calculus 1 was one of those theorems that you probably didn't spend a whole lot of time on, and it was one of those theorems that guaranteed a point existed. And any time in math you can guarantee that something's going to happen, that's kind of a big deal. Like, I can guarantee you're going to have homework on this section. You know, so you don't have to wonder, is he going to assign homework or not? I know it's been bothering you. Yes, you will have homework on every section. But the mean value theorem for integrals says that somewhere between the two rectangles, one that goes above and one that goes below, there is a rectangle whose area is precisely equal to the area of the region under the curve. So somewhere in between that rectangle that goes above the curve and somewhere in between that rectangle that goes below the curve in that same position, somewhere between those two, there's a rectangle that would give you the exact area under the curve. Okay, and that's what the mean value theorem for integrals is in words. Technically, you know, if you have a function that's continuous on a closed interval from a to b, then there exists some number c, which is an x value, some number c in the closed interval from a to b, such that the integral from a to b of f of x dx is equal to f of c times b minus a. And again, what does this actually mean? That somewhere between that, what your book calls it is a inscribed rectangle and a circumscribed rectangle. The one that's too big, that's inside, that's too small, and the one that's larger, that's on the outside of the curve. Somewhere between those two, there's a value such that there exists a rectangle that would give you the exact area under the curve. Okay, and you may want to read through that theorem if you're a math major. It is a very powerful theorem. It's something that you will definitely revisit down the road if you are a math major. The average value of a function, I usually do not spend a lot of time on that. Real quick, I'll go over the formula for the average value of a function. You don't have to write this down. You can if you want. The formula for the average value of a function is 1 over b minus a times the integral from a to b of f of x dx. Okay, so that value from the mean value theorem, that f of c in the formula for the mean value theorem, that is called the average value of f on the interval. You know, that place between not too big and not too small, that's the average value. All right, the second fundamental theorem of calculus. See, there's another one. Yeah, there's another one. There are a lot of things you could do with the second fundamental theorem of calculus, as far as proving wise, and just with straight just mathematical terms. But as far as you are concerned, I would think that the second fundamental theorem of calculus would be important to let you know, and you've probably already been told, that when you take an integral, you can then take the derivative of that of your answer and get what you started with. That's kind of what the second fundamental theorem of calculus hints towards. Here is in symbols, here's what the second fundamental theorem of calculus says. Of course, the function f has to be continuous on some open interval containing some value a. All right. Then for every x value in that interval, the derivative of the integral from a to x times f of t dt is equal to f of x. So to me, one real easy way to understand this, if you think about doing this integral here, and you find an answer, and then you plug in these two things, these two values, but then you take the derivative of that with respect to x, you're just going to you're going to just get that function of x. One way of thinking about this, again, would be like the derivative of an integral. It gives you the integrand, and it is a function of x because you plugged in x here. Where would the f of a go after you integrated? F of a would be a constant, and so when you take the derivative of that, it would go away. So again, there are a lot of cool things you could do with the second fundamental theorem of calculus. To me, though, it's just a way of saying, hey, I know whenever I take this integral, if I take the integral and then take the derivative of that, I should get that original function that I started with.